Hey everyone, today let's solve this problem called minimum time to make array sum at most x. So in this problem, you are given two zero-index integer arrays nums1 and nums2 equal length, and every second or indexes in the nums1, the value of that will be incremented by nums2 of that same index. And after this is done, you can do the following operation, which is to choose an index or index basically, and make the value of nums1 to be 0, and you're also given an integer x, and you want to know what is the minimum time that we can make the sum of all elements of nums1 to be less than or equal to x, or a -1 if it is not possible. Let's see some examples to illustrate the idea. So in this example, nums1 is 1, 2, 3, and nums2 is also 1, 2, 3, and x is 4, and the output is 3. Let's look why. So for the first second, we apply the operation of I equals 0. So basically, every element in nums1 add the value in the nums2 of the same index. So this 2 plus 2, because this 2 and this 2, they have the same index, and this 3 plus 3 is this 3 and this 3. And because we choose to do the operation on I equals 0, so this will become 0. So that's why the output is 0 for 6, which is not the end of the operation, because the sum of 0 for 6 is 10, but we want x is 4, which is less than or equal to 4, which is not true, so we have to keep going. So for the second operation, we apply I equals 1. So prior to that, the result was 0 for 6, and 0 will plus 1 because the 0 index is 1 here, and then the second element will be 0 because we apply the operation on the second index, and the third index will be 6 plus 3. 6 is here coming from, and then 3 is coming from here. So we have 109, and the sum of 109 is still 10, which is not less than or equal to 4. So still not true, we still have to keep doing. For the third operation, we apply that on I equals 2. So nums1 now become 1 plus 1, 1 coming from here, another 1 is coming from this nums2, so we become 1 plus 1, and then 0 come from the previous result, which is 0, so plus 2 is coming from the second index, and this will set as 0 as well because we're applying the operation on I equals 2. So now if we look at the sum of this array, it will be 4, which is less than or equal to 4. So we operate 3 seconds, and this is the optimal answer as it happens, so we just return 3. So that's basically all for the problem description. Now let's see how can we actually solve the problem. Okay, looking at this example, the first thing to notice is that it's not always beneficial to make more operation. For example, nums2 here is 1, 2, 3, but I can change it to like 99, 99, and 99. And for operation equals 0, it means we don't do any operation. The sum of this will be 6. But if I set nums2 equals to 99, 99, and 99, then even one operation will make the sum very large, much larger than 6. So it is not always better to perform more operation. So it means that we pretty much cannot do binary search here, because sometimes it is better to perform less operation. So that's basically the first observation. So the second observation, or the second question that you want to ask yourself, is that is it necessary to perform I equals something twice, or 3 times, or 4 times, or 6 times? Doesn't matter. So does it make sense to apply I equals 0 more than once in the example? So the answer is no. If you think about it, operation I basically means set I to 0 and everything else increase. So by increase, I mean the number in the nums2, but it doesn't matter. So let's see what happens if I apply the same operation twice. So let's assume there is an optimal answer where the optimal answer somehow perform this operation I twice. So operation, let's say 2 will increase the 0 index element and increase the 1 index element by the value of nums2, and set the index 2 to 0, and then similarly set everything else to increase based on the value in the nums2. So this will look something like this, and then we will do a bunch of operation, and then somehow, because we assume that it is possible to repeat itself, so we're gonna do the same operation operation again in here. Now, if you think about it, after certain operation, we will get our final answer having the sum less than or equal to x, for example. And this operation 2 appeared twice. But if you think about it, you can pretty much remove this operation 2 here. Basically, the first operation 2, we can pretty much remove it here. It doesn't affect the later result because this 2 will set to 0 anyway in here. And if we don't do this operation 2 here, this value will be even smaller. So if there's an optimal solution with duplicate operation index, it is always better to just remove the first duplicate and achieving an even smaller sum at the end. So what I'm trying to say is that it's not necessary to repeat the same operation. So what does this tell us? It tells us that at most an operation will be done for each index. Either include that in the operation or ignore that in the operation. That's basically two possibilities, and at most in total an operation will be done at most. So that's our second observation. Well, we already got the answer that at most an operation that will be performed. So the next question, naturally you would think, what order should we pick those operations? Because the order does matter. So let's assume that we're gonna apply the operation 3 times, and for this particular example, because we know that the operation index will not repeat itself in the optimal answers, so the first that does the operation will have a nums 2i times 2, and the second index that does the operation will have a nums 2i times 1, and finally the last one that does the operation will have a nums 2i times 0, which is just 0. So notice that I don't mention the value of nums I because it doesn't matter. Once it is decided that we should perform operation on that particular index, the value of nums I never matters. So I just talk about the value of nums 2. Now we know that in general one index of all the selected index must appear OP minus 1 time, and one must appear OP minus 2 times, and one must appear OP minus 3 times, and all the way to 0. Then it is natural to choose the smallest to appear the most, while the larger appear the least. So for example, in here 1, I want it to appear the most, which is 2 times, and then for 2, I want it to appear 1 time. So it's here, and then for 3, which is the largest, I want it to appear 0 times. That's why. If we apply 3 operation, we can get this array like this. So in other words, we want to sort all the values by nums 2, and that would tell us the order of the operation. Now we know what order should we pick. That is the natural next question to ask. What should we pick them in this order? So basically we can apply some DFS. Fi remain means from I all the way to the last one, what is the minimum if remain operation must be done? So from there, we can do some recursion, either to include it or to ignore it. So by including the current index interselected, it means that I will select the current index in the operation. Basically, I will apply operation I somewhere, or we can just ignore it. It means that we don't apply any operation on this index. So basically, we kind of first that and get the minimum of 2 possibilities. So because we know that we at most will apply an operation, so we can do something like for I in 0 to n. So basically we can do 0 operation or we can do an operation, and if f0 and I is less than or equal to x, then we just return I. So that's basically the flow of the algorithm. Of course we need to do some math inside the fi remain function and to calculate the shifted result. But basically this is the main flow of the algorithm, and I will show more in the code implementation for details. So first I'm gonna put the value in nums1 and nums2 in the same array because I want to sort the whole array based on nums2 as we mentioned. So I'm going to initialize n as the size of the array, and then I'm going to sort the whole array based on the value of nums2. I want the greatest go first, so I also need to store the sum of nums2 that I'm going to use later. So I also need the infinity. So I'm going to start writing the recursive function first. So in line 13 is just a smart way in Python to automatically automatically apply DP. So in line 14, which is the recursive function, I means the current index, and then remain means that there are how many operations that we have to do. So first, just gonna check some boundary. If I equals 0, it means that we don't have anything else considered, or the remain operation is less than 0, which means that we do more operation than necessary, or remain greater than the remain length. Basically, it means that there's no way that we can fulfill all the remain operation because we don't have enough remaining element starting from I all the way to n-1. So in this case, we can just return 0 if remain is 0. Otherwise, we just return infinity because it is not a valid case. And in line 17, this is the first scenario. If we gonna include the current index, then we can offset the value by its remain time. And after doing this operation, we can recursively call I plus 1 and remain minus 1 because there's one less operation that we have to take care of. And otherwise, we can ignore that, which means that we don't apply any operation on this index I. And in this case, we will just add the value of the nums I and then recursively call I plus 1, and remain will stay the same because we don't do any operation. So there's basically just two possibilities that we can do for this index, and we're gonna brute force them and get the minimum out of them. So now, because we know that it's at most gonna perform an operation, then we're just going to loop through every possible operation. So the preset value is nums2 sum times OP. So I did this because I'm just gonna assume every element apply OP amount of time first. Then I'm gonna offset it in line 17 if I choose this element to be included in the selection that I'm gonna apply operation on. So because we are sorting by the value of num2 and the larger will come first, so this offset will give us the lowest possible. So now if this value is less than or equal to x, then we're just going to return OP, because if OP works, current operation works, we don't have to check for operation plus 1 because we want the minimum operation. And if all operations are not doable, then we're just going to return -1 at the end. So for the time complexity, it is O(n) squared, mainly coming from the recursive call here, because I can go up to n, and then remain, as we mentioned a couple of times, the remain operation can go from 0 to n, so it is n squared for this recursive call because we apply cache on it. And for the space, it's similar because we have to catch this result. So this is going to take us n squared space as well. So that's pretty much all. Let's try to submit it. Okay, accepted. Again, I will include a text version of this whole solution in the description box below. And I hope you enjoy and learn something, and I will see you next time. Bye bye.